Hello and welcome to today's webinar. My name is Peter Simon and I am a product manager at QATM. I am very pleased that you are here today in this webinar. I would like to look at the topic of metallographic hot mounting at its limit. I'm going to give you an insight into the hot mounting press and will discuss how to make this process faster and more cost effective. I will show you some interesting application examples and also address possible errors. Of course, I will present you some beautiful micrographs and would like to show you how you can increase the safety level in the hot mounting process. I will also briefly discuss how you can mount some pressure-sensitive samples using a hot mounting press. During the webinar, I would like to give you the opportunity to ask questions. Please use the chat function of the GoToWebinar tool. My colleague and I will try to answer you in the chat during the webinar. If you have any further questions, we will be happy to contact you after the webinar to discuss your questions. First, a brief summary. We will start with the basics and ask ourselves why samples are mounted. Here I will show you some standard applications. I will discuss the topic of time and cost savings in detail with you, and finally I will address work safety and the mounting of pressure-sensitive samples. Why hot mounting? Why are samples mounted? What are the options for bringing samples into a standard form? What does it look like in practice? I would like to address the why question first. Samples in material testing can have very different shapes and geometries. These may include sharp-edged sample segments, very small geometries, thin foils, or even balls, which can be better handled and prepared after mounting. Another reason for mounting is the protection of sensitive samples. For example, if I have a sample with a brittle layer that must not be damaged during the preparation process, mounting serves as protection. In addition, mounting makes it possible to group several samples into one sample mount, as can be clearly seen here in this picture. If I want to analyze a sample at the edge area, I need a especially flat sample preparation. Here too, mounting is often necessary. Furthermore, mounting gives my samples a standardized shape, which enables automated preparation using semi or fully automatic machines. There are different methods available for mounting samples. In a classic cold mounting process, a mounting compound consisting of several components is mixed and poured into a mold. The individual chemicals must be combined in a specific ratio and cure within a defined time. Depending on the cold mounting material used, the appropriate safety level must be observed. The size and geometry of the sample are depending only by the shape of the mold. The cold mounting method is suitable for small quantities of samples, porous materials, and complex geometries that require vacuum infiltration, as well as for temperature-sensitive samples such as those commonly found in electronics. A new method in material testing laboratories is UV mounting. Here the process is very straightforward a single component resin is poured into a UV transparent mold and cured in a UV mounting device within a very short time. The mounting quality is somewhat limited, so this method is best suited for simple sample geometries and standard applications with lower quality requirements. A key advantage is the very short curing time of just 60 seconds. Now let's turn to the main topic of today's webinar, hot mounting. This method is especially popular for applications with high sample throughput and high quality requirements. With a modern hot mounting press, the cheap granulate can be cured into a solid sample within a short time, in best case about 4.5 minutes. Operation is simple, and thanks to the high pressure, flat and parallel sample mounts with excellent adhesion between mounting material and sample are produced. We will take a closer look at the hot mounting process in the following section. Using a video, we as machine manufacturer provide you with an inside look at a hot mounting press to help you better understand the process. This can be very helpful if you want to mount samples efficiently and improve the process. The mounting press features a closed press chamber into which both the sample and the resin are placed. The press chamber can have different diameters, allowing for a production of mounts in various sizes. The sample is positioned on the lower piston, which can be moved up and down with a hydraulic system. Next, the mounting material is added and the press chamber is sealed. Once the process is started, the resin is compressed, heated, and cured into a solid mount. As a machine manufacturer, we strive to keep the system's thermal mass as low as possible and to optimize the heat transfer of the heating and cooling systems. In recent years, we have made significant technology improvements, making the process not only faster but also more efficient. After the sample has completed the heating and cooling cycle, it can be removed from the hot mounting press for further preparation. There are different mounting materials that can be used in a hot mounting press. Basically, these can be divided into three main groups: epoxy resin, phenolic resin, and thermoplastic resin. Epoxy resins and phenolic resins both cure through a combination of heat and chemical reaction in a hot mounting press. Epoxy resins offer very good adhesion to the sample itself and to the fillers contained in the resin, resulting in a minimal gap between the mounting material and the sample. Due to their high filler content, epoxy resins also achieve a high hardness, making them well suited for mounting hard materials as well as for subsequent grinding and polishing. Phenolic resins are simple in composition, but they also have a chemical reaction during the hot mounting process. Phenolic resins have good mechanical properties and are cost effective. Even with a lower filler content, they can deliver very good results for standard preparation tasks. Finally, there are thermoplastic resins. These resins cure through the application of heat, there is no chemical reaction involved. Thermoplastic resins also offer the possibility of producing transparent hot mounts, which can be used for certain applications. Epoxy resins are often used when very hard materials need to be prepared, meaning materials with a hardness greater than 800 HV. They are also used for edge examinations where low gap formations and high edge sharpness and flatness of the sample are important. Typical examples include hardened steels, coated parts, nickel-based alloys, ceramics, or samples where hardness profiles need to be measured. We offer different types of epoxy resins. There is a standard black epoxy resin and also the EPOMAX, which has a shorter mounting time and requires less cleaning, meaning it sticks less to the press pistons and the press mold. Here is a standard example of a standard application using epoxy resin. A part of a gear wheel with nitrided layer coating was prepared and mounted in a diameter 40 mm. The aim of the examination was to measure the thickness of the nitrided layer and to perform the NHD hardness test. This gear segment was mounted at 190 to 200 degrees, heated for 3 minutes and 30 seconds at 250 bar, and then cooled for 3 minutes and 15 seconds. So the mounted sample was ready. After 3 grinding steps and 1 3-micron polishing step, the sample was fully polished. It can be seen that the layer was well protected during the mounting and a sharp-edged preparation was possible because the epoxy resin is very hard. This allowed the measurement of the nitrided layer. Here is another example related to epoxy resin, focusing on the analysis of a martensitic steel that was coated with a tungsten carbide cobalt layer using high-velocity flame spraying to improve the wear resistance and the temperature stability of the material. Usually, this sprayed layer is analyzed in cross-section, measuring both the coating thickness and the porosity to assess the quality of the coating. Precise sample preparation is especially important to avoid chipping of the coating and to measure the porosity accurately. The relevant sample segment was mounted with the epoxy resin using a hot mounting press with a hot mounting time of in total 7 minutes. Preparation then followed the DVS standard using only grinding steps with diamond grinding wheels up to a grid size of 3 micrometer. Polishing with diamond particles was avoided as it could destroy the measurement of the porosity in the tungsten carbide cobalt layer. After the final grinding step with the Polaris M with 3 micrometer diamond grinding wheel, only oxide polish with Epoxyl F solution on a corresponding omega polishing cloth was used. The excellent sharp-edged preparation results achieved in this way and a perfect analysis of the coating was done. Phenolic resins, also known as bakelite, are preferred for mounting soft to medium hard materials, typically up to maximum hardness of 800 HV. They are particularly well suited for microstructure examinations in the core area as well as for routine mounting tasks. QATM offers 3 different phenolic resin-based mounting materials red, green, and black. Technically, the choice of the color does not significantly affect the quality of the mount. However, it allows for easy color coding um, in the lab of various sample types. Typically, application areas include unhardened or low alloy steels, weld seams, non-ferrous materials such as aluminum alloys or brass samples. In addition, phenolic resins are often used as a cost-effective filler material in combination with epoxy resins. More on this topic later. Here is a standard application example for non-ferrous metals and mounting with phenolic resin. In this case, we have a wire segment made of an aluminum alloy. The goal is to analyze the microstructure of the aluminum wire both in cross-section and in longitudinal section. For this purpose, the wire segment was first separated and then mounted in bakelite black. Mounting was carried out with a temperature of 200 degrees, a pressure of 250 bar, and a heating time of 3.5 minutes, and a subsequent cooling time of 3 minutes and 15 seconds. Sample preparation included 2 grinding steps with SiC paper with the grid size of 600 and 1200, 2 polishing steps with 3 micron and 1 micron, and the final polishing step with Epoxyl F. To see the microstructure, either a sodium hydroxide solution or an electrolytic Barker etching was used. Both methods enabled a reliable microstructure analysis. In the second application example, I present a classic weld seam. On this weld seam, both a hardness test and the usual measurements were performed, including penetration depth, penetration width, and the A dimension. After cutting, deburring, and cleaning the sample, it was mounted in black bakelite. Mounting was carried out with a maximum temperature of 200 degrees, with a heating time of 3.5 minutes and a cooling time of 3 minutes and 15 seconds, and a pressure of 250 bar. The sample was then ground in 2 steps using a metal bonded diamond grinding disc with a grid size of 54 micron and 10 micron. These diamond grinding discs, called Vega, achieve a very high removal rate and deliver excellent results in a very short grinding time. This was followed by a 3 micron polish, and after etching with 3% nital solution, the microstructure could be analyzed and we had perfect results. Now let's turn to the thermoplastics. In hot mounting, their primary use is as a filler material for sample labeling. The sample is first mounted in an epoxy or a phenolic resin, then labeled with a tag, and finally covered with a small amount of thermoplastic. The high transparency of the thermoplastic is very suitable for this purpose. In addition, fully transparent mounts can be produced using thermoplastics, which is especially used for soft materials because thermoplastic resin is very soft. So assemblies or complex geometries or soft materials can be mounted with thermoplastic resin. These mounts are particularly well suited for target preparation because of their transparency. Thermoplastic mounting material is available as a fine-grained powder. Typical examples of soft materials that can be mounted with thermoplastics include non-ferrous metals like copper alloys or soft iron. Now that we have covered the basics and standard applications of hot mounting, let's address the question of how to make this process as efficient and cost-effective as possible. I will discuss this aspect of the webinar in more detail and hope to provide you with some useful ideas for your laboratory practice. A very simple and effective way to save time and costs is multiple mounting. With certain hot mounting press, you can mount two samples simultaneously stacked on top of each other within a single press chamber. In addition, modular systems are available that allow up to 4 mountings to be carried out independently and in parallel. I will explain the double mounting on left side with a single press mold in more detail on the next slide. Machines designed for double mounting are typically equipped with a tall press cylinder as standard. In this press cylinder, the first sample and the mounting material is placed at the bottom. A spacer piston is then inserted here, and a second sample with a corresponding resin for the second mount can be added. The height of each finished mounted sample is limited to around 15 millimeters, which is sufficient for most applications. A key advantage is that the spacer piston is very cheap, and this method allows you to quickly and easy double the sample throughput in your lab. I have prepared a simple example of double mounting for you. In this case, I mounted a nut with the size of M12 in epoxy resin. The mounting material I used was Epomax. Epomax enables short process times with a total mounting time of just 4.5 minutes. In the example below, I did double mounting using the same parameters, but in the same time I mounted two samples. The insertion of the spacer pistons must of course be taken into account in the time comparison. That is placing the piston, inserting the second sample, and adding the mounting material for the second sample. But overall, however, the total time with double mounting was reduced by 40%. Another way to shorten mounting times is by using modern hot mounting presses. With the help of thermal simulation, both the machine design and the temperature control can be optimized according to the latest technology standards. In addition, new machines feature a preheating function that allows the press chamber to be preheated before the process begins, further reducing the heating phase. Overall, this can reduce the mounting time by up to 35%, while also lowering energy consumption by approximately 10%. We encourage you to check and improve your process times. Many people use standard settings that have not changed for years, but the technology and the mounting materials are better now. Machine type, sample diameter, and the mounting material all affect the best settings. The size and material of your sample are also important. We are happy to help you to find the right settings for your needs. If you want, you can send your sample to our application laboratories and we will suggest a preparation method for you. As already mentioned, the mounting process can be divided into two phases, the heating phase and the cooling phase. One way to optimize the process is to shorten the heating time. If you start reducing the heating time, you will notice um, at, at what point the mounting material is no longer fully cured. If after mounting you see unmelted grains or a cloudy area in thermoplastic resins, you reached the minimum heating time, and in this case you have to slowly increase the heating time um, to remove these problems. A simple test is also helpful. Use a cloth and some ethanol to check the chemical resistance of the phenolic or the epoxy resin. If the surface of the sample becomes dull or discolored, you should increase the mounting time to remove these effects. You can also briefly test the sample in etching solution to check its resistance and find the best process settings. If you sometimes get poor quality, the problem might be the mounting material itself. Many mounting materials are hygroscopic, which means that they absorb moisture from the air, and wet resin needs a longer heating phase to cure completely. So always store your resin in a dry place and keep containers closed. Sufficient cooling is very important to the hot mounting process too. So if you want to shorten the cooling time, you need to be careful. But you can see it on your samples. If you have too short cooling time, you can see bubbles or um, cracks. Um, so then you have to increase your cooling time until these effects are not there. Another tip from my side, please check your cooling system time by time because um, if your tubes in your water system or inside the machine are clogged, then you have to descale your system, your water system, and this can affect your cooling system and show you or give you problems if you have bad cooling performance. Depending on the water quality in the freshwater system in your lab, lime deposits will build up over time in the water pipes and possibly inside the machine. These deposits reduce the pipe diameter and, as a result, decrease the flow rate of the cooling water. Similar to a coffee machine, we offer the option to measure the water hardness during the installation of the machine and to set a suitable descaling interval for a regular cleaning of the cooling system. Supplied descaling tablets and an integrated descaling function in the machine software make this cleaning process easier. Alternatively, you can use a maintenance-free recirculation cooling system to cool your mounting press efficiently. The heating and cooling times in hot mounting are limited by the low thermal conductivity of the mounting material. Usually, the resin has a much lower thermal conductivity than the sample itself. To reduce the process times, the heat path through the resin should be kept as short as possible and the highest possible thermal conductivity to the sample should be ensured. For metallic samples, times can be significantly shortened by reducing the amount of mounting material, choosing the smallest possible mounting diameter, using suitable sample dimensions, and maximizing the contact area with the press cylinder. If you also consider the subsequent preparation step in addition to mounting, the total processing time for the sample can be further reduced by using a press piston with an integrated chamfer. Samples mounted in this way no longer need to be manually chamfered on a grinding disc after removal. This eliminates the manual preparation step and saves time. It is also possible to combine different mounting materials to reduce the cost of consumables. If a sample requires the use of a high-quality epoxy resin, this can easily be combined with a more affordable phenolic resin as a filler material. In my example, I first used 3 scoops of epoxy resin. So the picture on the left side, the black sample. In the second step, I used only 1 scoop of epoxy resin and then filled the rest of the press chamber with 2 scoops of bakelite. One example with green or with red bakelite. Since epoxy resin is about 3 times more expensive than bakelite, this approach saved around 40% of the material costs. In metallography labs, you see very often beautiful colored samples, and they are not only beautiful but also cost efficient. When combining materials, then the mounting times are usually based on the material that requires the longer heating and cooling phases. It is also possible to combine several samples in a single mount. This allows the samples to be mounted and prepared together, saving time and resources. When doing this, it is important to mount materials with the similar properties together and to maintain sufficient distances between the samples and as well from the edge of the mount to prevent cracking. On the left side, you can see some successful examples, while on the right side there are samples where the proper spacing was not observed. Let's move on the next section of the webinar. How can occupational safety be improved during the hot mounting process? Our hot mounting materials are continuously improved. In the last years, various substances in our product range have been replaced. For example, hot mounting materials containing boric acid have been replaced and dialphthalate has been removed from the range. This ensures compliance with current regulations. However, hot mounting materials can still contain hazardous substances and fine dust. Our hot mounting presses provide a patented solution for extracting fine dust during handling, making the mounting process safer. The extraction system can also be used for cleaning the machine and the work area. Finally, let's take a brief look at the last point of the webinar, How can pressure-sensitive samples be mounted using a hot mounting press? First, it's important to clarify what is meant by pressure-sensitive samples in this context. There are clear limits that make it impossible to mount certain types of samples using a hot mounting press. However, there are cases where very good results can be achieved, such as with thin-walled tube sections, shells, thin sheets, and coated or painted sheets. For these types of samples, the heating phase can be divided in two steps. In the first step, the hard granulate particles are melted at low pressure. In the second step of the heating phase, compaction takes place at a higher temperature and increased pressure. This method helps prevent deformation of thin-walled tubes or sheets and avoids damaging coatings. I will conclude with a short application example for this purpose. In this case, the sample was a graphite plate coated with a very thin metal layer of about 100 micrometers. The goal of the laboratory task was to mount this material combination and to prepare it without chipping or cracking, with special attention given to the examination of the thin metal layer. This approach was intended to ensure that the sample preparation process would not influence the results. On the left, you can see a sample segment positioned in the mounting press using a sample holder. The samples were mounted in different sizes using the two-step mode. In the first step, the epoxy resin was melted for 5 minutes at 120 degrees and only low pressure of 5 bar chamber pressure. In the second stage, both the temperature and the pressure were increased to 200 degrees and 200 bar, and the sample was fully cured. After a cooling time of 3 minutes, the sample could be removed and then polished down to 1 micrometer using 1 grinding step and 3 polishing steps. Microscope images of the metal layer clearly show that the coating was not damaged during the mounting and during the preparation, and it can now be analyzed without artifacts. In comparison, using a one-step mounting process destroys the metal layer, making the analysis impossible in that case. Let me conclude by summarizing the key points of this webinar. At the beginning, we discussed the hot mounting process and looked at typical application examples for different mounting materials. We then focused in detail on how you can save time and costs during the mounting process. I introduced double mounting and multiple mounting, and we also saw that modern technology in hot mounting presses can lead to additional time savings. I motivated you to review and optimize your mounting times, and we reviewed common mounting errors, and I explained how we can avoid them. Regular maintenance and descaling of the cooling system also contribute to increased efficiency. Proper sample sizing, mounting with a chamfer, and combining different mounting materials offer further savings potential. Combining several samples in one mount is a proven way to increase efficiency in the metallography laboratory. Finally, I explained how using an extraction system can improve safety in the lab, and the advantages of the two-step mode for mounting pressure-sensitive samples. I hope this webinar has provided you with ideas to make your daily laboratory work in mounting even more efficient and safe. I would like to thank you for your attention and for listening up to this point in this webinar. Please keep an eye on our newsletter, where we will invite you also to the next webinars. I'm very pleased to have you here in this webinar today and wish you all the best and a nice day. Goodbye.